Is the screen visible? I
Yes,
have
yes,
now
yes.
done full screen.
It is in full screen, perfectly fine. Yeah.
Okay, all right. So I'm going to talk about hydrogen and fuel cells in general, but I'm also going to touch upon hydrogen and fuel cells in UAVs/drones, why we are looking at this technology option, why it is important, and what are the sort of the challenges or the opportunities therein. Okay. So as I said, please stop me whenever. And I am a faculty at IIT Gandhinagar. I'm in mechanical engineering, and recently, as Professor Abhishek introduced, I also co-founded a startup company on campus. So this is our laboratory at IIT Gandhinagar. This is a hydrogen safety laboratory. It is equipped with the right kind of air ventilation and hydrogen leakage detection and other safety systems that are required to handle hydrogen, carbon monoxide, and hydrocarbons all at the same time. And this is one of the facilities that we developed over the years, and this is where we work, right? And just give you a glimpse of what we have developed so far. We are a very applied laboratory where we apply a lot of the science and technology to realize prototypes and then demonstrate these prototypes, much like Professor Abhishek and his laboratory and his research team. So what have we done so far? Highlights of our research, which have actually resulted in prototype demonstrations, proof of concept studies, and so on, is we have developed at TRL6 with collaboration with Thermax, DST, and Reliance Jio, a replacement of a diesel generator for telecom backup power. So telecom backup power is one of the largest consumers of diesel in the country.
Inside photos.
Just to give you an idea, diesel generators consume about 17%, 17% of the total diesel consumed in the country, and they are the second highest diesel consumer as a group, right? And just to give you an idea, the biggest one is the transportation sector, which is 70%. And the second one is 17, which is the diesel generator. So, and one of the things where diesel generators are used very often is cell phone towers. There are about 6 lakh cell phone towers, and with 5G, they are expected to go up to 14 lakh towers. And the grid is not very reliable in India. And so we developed this technology to have a methanol powered fuel cell system that is more than double the efficiency of a diesel engine, has nearly half the CO2 emissions, and is cost effective, and also it does not rely on imported diesel, which also gets stolen, by the way, in many remote locations. So it was a proof of concept demonstration, first of a kind in India, that we had done in collaboration with these other organizations. So that is one of our achievements. And the second one is we have developed a strategy for strategic applications. We have developed a hydrogen generator, an onboard hydrogen generator that works on logistic fuels like diesel and JP8. It is also capable of working with other fuels. So basically, any fuel you throw at it, it is capable of converting it to hydrogen. It is mostly meant for land-based as well as for certain naval applications, which I will not go into too much detail right now. But we have developed this at TRL4 with the collaboration with the DRDO and other important projects such as Imprint and so on. And we have developed it at a 30 kilowatt prototype at an 82% efficiency. And this is something that is not available in the open literature. At least we have not found somebody who has done this. Of course, there are variations of this available with 2 or 3 countries worldwide. But again, that is not in the open literature. We just know that they have the technology. Now, we have also developed something to test fuel cells. And typically these are imported and these are very expensive. So we have developed a world-class alternative to imports from North America, East Asia, and Europe. And in some ways we have features that are not available in imported test equipment as well. So this is what we do. And so this is in a nutshell. What is it that we work on? I think if we were to put it in one slide, this is what we work on. We make a platform. We make a platform that is to some extent versatile and robust to fuel input. right? So some places you have methanol available, some places ethanol, some places ammonia, CNG, bio-CNG, diesel in case of strategic initiatives, and others, right? And people are talking about green hydrogen. You might have heard of it, but it's not yet available. And so there is some uncertainty and sort of unpredictability with respect to fuel availability. So we want to make our system robust to that particular aspect. And our platform is that. So what we do is we have an internal converter that converts the available fuel input or hydrogen carrier input, as I will show in the slides, coming slides, into hydrogen on board, on demand, and on site. And therefore, we are able to use fuel cells where previously fuel cells would not have been able to use because of lack of availability of hydrogen. And of course, that fuel cell is tied to something called balance of plant, which I will show in a moment. And then so you get double benefit in the sense that you get electricity, of course, but you also get waste heat from the fuel cell stack, and this waste heat is at a high enough quality that it can be used for heating or for cooling. And so for those of you who are not familiar with mechanical engineering background, you can also use waste heat to actually cool. It appears very counterintuitive, but it can be done. These are called vapor absorption refrigeration systems, and these are now becoming commercially viable. And so when we couple it with that, this high grade waste heat can be used to cool as well. So we have a very good platform now for various applications, including for stationary, stationary power, that is replacement of diesel gensets and other types of backup power and so on. Even for e-mobility, we can think of this as something that is powering a refrigerated truck or a refrigerated railway carriage, things like that. We also can think of this as something that extends the range of a battery vehicle. And why you should extend the range of a battery vehicle, I'll come to in a moment. So, and also in aviation, of course, in aviation, there are some simplifications that we need to make, and these HVAC systems, etc., might not be, it's too bulky and too heavy to carry. And so therefore we might have to make some changes to this platform. So this is the background of what we do. Now, fuel cell, right? So I'm told you are students, so I'll just briefly describe what a fuel cell is, and also hopefully bring out what is it that is different between a fuel cell and a battery, right? So for example, what is a simple fuel cell? So simple fuel cell, one of the examples that I can give you is called a polymer electrolyte membrane, PEM fuel cell. That is what you see on the right, the figure. It's called PEM, polymer electrolyte membrane. Okay. So what is this? So this basically, you can see the gray one, that's basically a membrane, right? It looks like a polyethylene sheet. That's basically what it is. It's a different kind of polymer, but it's a polymer nonetheless. It looks like a polyethylene, transparent white polyethylene sheet. That's all it is. And what it does, it's selectively permeable to H plus ions. Okay. So if you have an excess of H plus ions on one side relative to the other, the H plus ions can go through this membrane and show up on the other side. Now, it's not permeable to other things, including to molecular hydrogen. So hydrogen cannot actually go through. Hydrogen ions can go through, but not hydrogen itself, right? So either whether you're talking about molecular hydrogen or atomic hydrogen, it cannot go through this membrane. Similarly, on the other side, you have oxygen or nitrogen, whatever it is, that cannot migrate to this side. Of course, there's a small migration that happens in reality, but I'm saying, as a concept, nothing else can migrate. Only these H plus ions can migrate. Why? Well, that's the chemistry of the membrane. That's how it's engineered. Okay. Now, what happens is you have two sides to this membrane, and on one side you supply hydrogen. Okay. So let me try to see if I can convert this to yeah. So on one side you supply hydrogen, one side of this particular membrane, and this hydrogen splits into hydrogen atoms, H and H, and each H gives up one electron and becomes H plus. Okay, so it becomes H plus, and therefore H pluses are on the left side of this membrane but not on the right side. So H pluses can migrate in through the membrane from the left to the right, or in other words, from the anode side to the cathode side. On the cathode side, there's oxygen available because air is being supplied or oxygen is being supplied. And oxygen again splits to oxygen atoms, and oxygen atom gains 2 electrons to become O double negative. Okay. O double negative combines with 2H plus ions and it forms water, right? 2H, 1 positive, that is 2 plus charges, and 1 double negative charge, O negative. So it becomes H2O, which is water. Okay, and water is the byproduct and it comes out, right? And some of the oxygen that is not used also comes out on the other side. Similarly, hydrogen, not all of it gets used, most of it does, but some of it does not, and that hydrogen comes out of this side. Okay, so now you have, this is how a fuel cell works. So now you might ask, this is all very nice, but where is the electricity, right? So now the point is that these hydrogens, they gave up an electron. Why did they give up an electron? Because it was thermodynamically favorable for them to give up that electron, and so they did. And these electrons are connected through an electric wire. And remember that oxygen, I have to supply the electrons to the oxygen, and so therefore they need electrons on a continuous basis if I'm to continuously convert this oxygen molecule into oxygen ion. And so therefore I take these electrons from the anode side and I supply it to the cathode side. Okay, and then that completes the circuit. And so that is flow of electrons. And when there is a flow of electrons, you call that electricity. So that is how the chemical energy in hydrogen is converted to electrical energy. So this is a direct conversion of chemical energy to electricity. So normally what would you do? For example, what you do in your bike or in your car, right? So you also have chemical energy there. Petrol, diesel, basically chemical energy, right? So what you do is you burn it. So you combust it, right? That's why it's called an internal combustion engine, right? You burn it and you get gases at a very high temperature and pressure, and that move a piston, and that piston is in turn connected to the wheel, and that's how the wheel moves. Or in sometimes that piston is connected to a generator, and that's how it generates electricity. So there are multiple steps here: chemical to thermal, thermal to mechanical, mechanical to electrical, right? So in this, some of you might know the second law, restricts the efficiency of thermal to mechanical, and that is where you lose a lot of the energy. And so therefore, this fuel cell allows you to circumvent that. We still have to follow second law of thermodynamics. There's no way around that. But the practical limitations in which devices can be designed and manufactured and run, this works out to be far more efficient way of doing it, which is direct chemical to electrical than going through chemical, thermal, mechanical, electrical. Okay, so this is the background. Any questions so far? Okay, if not, I have a question of my own. So what happens if I stop the flow of hydrogen in this whole setup? What happens if I stop the flow of hydrogen? What happens to the fuel cell? Okay, looks like it's evening and you're not active. So the point is that when you stop the flow of hydrogen, the fuel cell stops. It's just like cutting off fuel supply to your bike engine or to your car engine, right? It's the same concept. So when you cut off hydrogen supply or the oxygen supply, either one of them, then the fuel cell stops, right? It just stops. There's nothing that happens. It just stops. And you could also do the other thing, which is open the circuit, right? Open the externally connected electron flow, which is basically open the circuit. When you open the circuit, also the reactions stop, and it just has a voltage, but it has no current, right? And so the net reactions go to zero. Okay, so clear so far? Any questions? Please stop me at any time. So what is it that we are seeing in terms of fuel cells? Fuel cells are basically energy conversion devices, and here it's more sort of similar in concept to a car or a bike, right? Where or a diesel engine, right? Where the energy is stored externally. That is, energy is not stored within the fuel cell. It is supplied to the fuel cell in the form of hydrogen or another fuel for different types of fuel cells, right? And so the energy is stored externally. So in your bike, you have a petrol tank, right? And in your car, you also have a petrol tank or a diesel tank, right? So that is where energy is being stored. Where is it being converted? In the engine, and that is fuel cell. So fuel cell is a converter of chemical to electrical energy. It's only a converter, it doesn't store any energy, right? And so therefore, if you imagine I have a car, let's say a Maruti car with an 800cc engine, and I want it to go at 200 kilometers an hour, it will not do that, right? So, but if I want to do that, then what I will do is I will replace the 800cc engine with perhaps a 1.2 liter engine, and then try to go to 200 kilometers an hour, and then perhaps maybe I will succeed, right? So what did I do? I increased the power of the engine, right? And so therefore I was able to go faster. Instead, for example, if I have a Maruti car with 800cc engine, let's say I have to refuel every 600 kilometers, and I don't want to do that. So supposing I only want to refuel every 900 kilometers, right? Then what will I do? I will increase the capacity of the petrol tank. I will not do anything to the engine because I'm fine. I'm just still going, right? But I will increase the capacity of the petrol tank to a higher capacity so that I can go 900 kilometers between refuel. So what am I achieving in this? I am changing the power and the energy independent of each other, right? Because the energy is being stored in the petrol tank, the power is being converted from chemical to mechanical in the engine. So similarly here, whatever is supplying that external energy, if you increase the size of that, you achieve higher energy density or higher energy content of the system, right? Whereas if you increase the size of the fuel cell, you achieve a change in the power. Now, that seems kind of obvious, but contrast that with something that you're very familiar with, which is batteries. Now, battery is something where you also have the conversion and you also have the storage in one device. You don't have anything external except electricity connection, right? So you have converter and the storage within the battery. And which means that if you increase the size of the battery, you change the power, you also change the energy. Now, that might seem to be an advantage, but in this particular case, I'll show you why it becomes a disadvantage, right? So for example, if I want to go farther using my drone or UAV or whatever it is that I have, I want to go farther, which means I need more energy, which means I need to use a bigger battery pack, right? And when I do that, the power that the battery can provide also increases, but that power is useless to me, right? I don't need that power, but it's still available to me. And I have to pay the penalty in terms of bigger battery weight and bigger battery volume. Okay. So that is where there is a difference between fuel cell and batteries. In some, batteries are certainly advantageous because they tend to be simpler. And in some, batteries cannot do the job. And so therefore you need fuel cells. And that hopefully will come out during this talk, right? So also batteries and fuel cells, there is no battery versus fuel cell most of the time. Many of the times it's battery or fuel cell. They're not competing against each other. And even in fuel cell systems, in most fuel cell systems, you do need batteries either to start or to do something which which is required. So you typically hybridize it with a very small battery. Just like in your car, there is a battery, and that's like in your motorbike today. Most of the motorbikes and scooters, there is a battery as well. And also they're different in terms of stage of development. The batteries tend to be more developed as in terms of technology readiness levels, because there are so many more batteries that are being manufactured with relative to fuel cells. So the technology of manufacturing, quality assurance, cost, etc., are fairly advanced for batteries. They're getting there for fuel cells, but they are getting there behind batteries. And so I just have to be upfront with you and say that this is the situation, right? And so both of these are thought to be extremely important technologies in various aspects, including how to increase the amount of renewables in the total energy mix. So just to give you an idea, India consumes about 7,000 terawatt hour of total energy, right? Out of that, only 20% is consumed as electricity, 80% is consumed in other ways, including petroleum for transportation, biomass, etc., right? So only 1,400 terawatt hour is electricity. Now this 7,000 is going to grow to 40,000 terawatt hour in 2050. By 2050, that's not very far, which is 27 years from now. Now, our electricity grid today can carry 1,400 terawatt hour. Now, if we go to 40,000 terawatt hour, you can imagine what kind of growth in electricity grid we are talking about. And it is impossible that one grid carries all this energy. And it also makes it vulnerable to hacking, etc. So therefore, there are multiple energy vectors and energy networks that are required, and not just one. It's simply impossible to carry all this energy in electric wires. Okay, so a bit about hydrogen, right? So a lot of people have a lot of myths about hydrogen. Today, hydrogen, contrary to most people's beliefs, is not actually produced from sunlight. So the fancy idea is that you use sunlight to generate electricity, you use that electricity to split water and make hydrogen and oxygen. So that's nice. I mean, that would be nice if we can do it, and people are trying to do it. But most hydrogen today is manufactured from methane. That is, you take methane or natural gas, you react it with water vapor or steam, and you get CO2 and you get hydrogen, right? And there's a way to separate the hydrogen from the CO2 and then bottle it into various different purities and then sell it to different people who want the hydrogen, right? So the idea is that today hydrogen is being manufactured from methane and not from renewable sources. If it does, and when and if it does get manufactured by renewable sources such as solar and wind or biomass even, so that will be called green hydrogen. Today, there are various colors of hydrogen. I don't want to go into too much detail because that's not the focus of this talk. There's a gray hydrogen, green hydrogen, blue hydrogen, brown hydrogen, and so on. There's a very small percentage, as I said, which is produced by splitting water using electricity that is made from renewables. That is the ultimate goal, but we are not there yet. Okay, and where is it used? It is used in petrochemicals, it's used in fertilizers, it's used in many chemical industries as solvents, especially in the pharmaceutical industry. So sorry, not as solvent, sorry, it is used extensively in the petrochemical, fertilizer, and increasingly in the cement and the steel industry. I take that back, not in chemical industry. What is it about hydrogen that attracts people? First of all, it doesn't have carbon. It is a fuel that does not have carbon. Okay, and that is obvious because we want to prevent global warming, climate change, etc. Right? So, what is it? What is it that attracts us to hydrogen? It has the highest energy density among commonly available fuels, 140 megajoule per kg. Just to compare, diesel is only 44 megajoule per kg, whereas petrol is 40 megajoule per kg. Okay, so that's how, that's how much better hydrogen is with respect to energy content. But that's kind of deceptive. Why is that deceptive? Because it has very poor volumetric energy density. So if you compare it per liter, then hydrogen is extremely poor. You have 0.0125 megajoule per liter at STP, that is at standard temperature and pressure, if you don't compress the hydrogen, right? Whereas comparatively, diesel is about 40 megajoule per liter. So look at that number, 0.0125 versus 40. Okay, so what you got to do, you got to compress the hydrogen. That's one option. So it's compressed to 350 bar, it's compressed to 700 bar, etc., which makes it expensive. First of all, you've got to spend energy to compress it. Then there are special cylinders that cost a lot of money, and you need safety protocols to handle this. Not everybody can handle it, and so therefore there are restrictions. So there are other ways of storing hydrogen. There is direct chemical storage in the form of hydrides, which can store 2 weight percent. So that is, if your storage tank weighs 100 kgs, only 2 kgs out of that is hydrogen, right? Compressed hydrogen, 5 kgs out of 100 kgs are compressed hydrogen, right? And there are other ways that we will talk about. And what I showed you in the beginning is something that circumvents this problem. We work with methanol, with ammonia, which have 12%, 17%, 18% hydrogen carrying capacities. And that is why we work with these hydrogen carriers. So they are very, very energy dense. So in a meter cube or in a liter of this fuel, we can carry a lot more hydrogen. And in other words, we can carry a lot more energy, right? So that's why we work with these logistic fuels or energy carriers, and then convert it to hydrogen whenever we need it, and not store and transport the hydrogen. Okay, for aviation, sometimes we cannot do that, sometimes we can actually do it. Okay, cost is something that I will not go too much into. Okay, so where are hydrogens and fuel cells being used today, right? So for example, if you see the Amazons and the eBays, they are extensively switching these forklifts that they operate in warehouses to fuel cell operated forklifts. What are the advantages? The fuel cell operated forklifts go longer between recharges, and so that's very attractive. And also they're cleaner because you don't need to use, you have to use this in indoor environment. So you cannot use engines, you cannot use CNG or petrol engine to power this, because this is an internal atmosphere, indoor atmosphere, right? So you need battery. Until now most of these are battery, but now increasingly being replaced by fuel cell. Buses increasingly becoming popular for hydrogen fuel cell buses. Of course the cost is still high, and we are getting slowly fuel cells into very, very many applications, including the stationary power applications that I talked about. So with that, any questions so far? Any questions on whatever I have said so far?
There is one question which Dr. Sirohi has, actually Jayant Sirohi has put in the chat.
Yeah. In electrolysis, yeah, I'm reading it. Yeah, thanks. In electrolysis, we have to supply power to break water into H2 and O2. So in this case, what makes the opposite reaction happen? Okay, wonderful. So this is a very good question. So maybe what I will do is I will try to oops. Okay, my stylus doesn't seem to work. So in the interest of time, I will just verbally say it, and I wish I can, let me see if I can. Okay, seem to be able to do it. So if you look at on a coordinate, right? So let's say this is something called a reaction coordinate, right? And you have, this is the reaction that we're doing, right? So H2 plus half O2 gives you water, right? This is ultimately, this is the reaction that we are doing, right? So if you look at where water is, right, it's somewhere there in terms of, this is energy. So let's say this is some kind of energy. It's called Gibbs free energy. Let's call it delta G, right? So this is some kind of potential energy. You can say chemical potential energy, right? So this is where the product is, H2O. And if you see where energy, how much energy hydrogen plus half of oxygen molecule have, that's there. Okay. So that's half a molecule, right? So energy of hydrogen plus half a molecule of oxygen is here, whereas energy of water is here, potential energy. So given a chance, hydrogen would like to react with oxygen to go there, right? So that's natural. It's like rolling down the hill. So if you have something up at a height, it wants to come down. So we are coming down in chemical potential. So that is natural, which means it's spontaneous. It wants to happen. So even if you have, for example, a mixture of hydrogen and oxygen, and you put a spark, it can actually ignite and become water, right? That's natural. It wants to do that. But what I'm doing right now is not putting, not burning it, but putting a membrane in between, making the same reaction happen, but with some control over how fast it happens. And that is what is a fuel cell, right? Basically, I'm carrying out the same reaction, except I'm controlling at what rate the electrons are transferred from one place to the other. And so therefore, I'm controlling the speed at which this reaction occurs. So instead of going to thermal energy, it directly goes to electrical. That's all I'm doing. But chemical engineering wise, it's very simple. The Gibbs function, or the Gibbs free energy of hydrogen molecule plus half of oxygen molecule is higher. That of water is lower at the same temperature and pressure conditions. And so therefore it's natural for one to try to go towards the other. And that's a spontaneous reaction. If I want to do the opposite, I must supply the energy, which is why I have to supply electricity, right? To split water to hydrogen and oxygen, it's an energy intensive process. Whereas the opposite is the natural process that happens. So I'm not sure. Did I answer the question?
Okay, yeah. Yes, thank you very much. That's very clear. But
Yeah.
what about the energy required to remove that electron from the hydrogen atom? Because we
Yes.
have to create the ions, right?
So
for the reaction.
Yes, there is. Again, if you look at the individual reactions, again, on one side, right, for example, So if you look at, if you split it up again and say, okay, on one side I have hydrogen, right? So I'm doing this, right? I'm doing H gives me H plus an electron, right? Now, if you look at the energy of this H, it's somewhere there. And the energy of this H plus an electron is somewhere there. And that's why the H wants to go to H plus electron. Okay. So the H plus,
Okay.
because the H plus and electron are not together. The H plus is inside the membrane and the electron is in the current collector, right? So they're not at the same place. But if you look at their combined energy, it's lower chemical potential, not energy, sorry, chemical potential. It's lower than that of the hydrogen atom by itself, right? So therefore the H atom wants to go there. Of course, there is something which prevents it from going there immediately, and that is the activation energy barrier. So there's some energy that is required to jump. So there's jumping energy, that's called activation energy, that is very common in chemical reactions, right? So that much is required, but then you gain more than that when you go from H to H plus electron.
I see. Okay.
So that is why it becomes spontaneous.
Thank you.
And the
Thank you.
similar thing happens on the oxygen side as well.
Okay.
Yeah. So now you might, another philosophical question is, why do we do this in the first place? So if you are saying I want green hydrogen, which means most probably I'll get it from solar or wind to electricity and then split water to hydrogen and oxygen, then ultimately I'm again doing the same hydrogen plus oxygen to get electricity. Why am I doing all this? So the answer is same as what we take bath every day, right? We take hot water bath, which is basically from an electric water heater. Now imagine most of the electricity comes from coal. You heat coal or you burn coal, you generate thermal energy, you generate steam from that, you drive the turbine, you generate the electricity, you transmit it, you distribute it. Imagine the kind of losses that take place in all of these sort of conversions. And it gets to your house. And what do? You convert it into heat again, right? Which seems to be such a total loss and such a total waste of energy, right? But look at the alternative. Can you distribute coal and burn coal in your house? You cannot. It's not dispatchable, it's not safe, it's cumbersome, you don't have the time. The cost of doing that is much higher than the cost of doing all of these losses, which is why you live with it, right? So that is the answer to why we do this. Okay, so I'll continue if that's okay. Yeah. Okay, my slides are visible. Hello. Hello?
Yes, I
Yeah.
can see that.
Okay.
Yes, it is.
All right. So we did an exercise. I'll not go into too much detail. We did an exercise where we saw what is the energy required at various stages of one of the aircrafts that we were trying to analyze, right? So it turns out that while takeoff, that aircraft, this is a bigger aircraft. This is not drones or UAVs. These are bigger aircraft that can carry people. Not too many people, but people nonetheless. So 400 watt hour was required for takeoff. Climb is 17,000 watt hour and cruise is 146,000 watt hour for about 4 hours of flight. Okay. And there's certain energy requirements for descent and landing and so on and so on. So if we focus on this right here, which is the energy required for cruise, right? 146,000 watt hours. That is, 1 watt hour is 1 watt supplied for 1 hour. That's energy, right? So for 3.7 hours, so which means for every hour of cruise, you need 40 kilowatt hour of energy. Okay, energy, additional energy. That turns out to be 142 megajoule for every 1 hour increase in the flight time. This is not 1 megajoule per hour. This is megajoule for 1 hour of cruise time. Okay, so the heating value or the calorific value or the energy content of hydrogen is 142 megajoule per kg, which and useful because I have a conversion from hydrogen to electricity. So that's, let's say, is 71 megajoule per kg, right? That means I need 2 kg of hydrogen for 1 hour of cruise time. Now, as I said, this hydrogen is compressed to 700 bar and stored in a cylinder, and only 5% of that weight of that cylinder is hydrogen. Okay. Now 5% of the weight is hydrogen, which means for 2 kg hydrogen, I need to carry a cylinder which is 40 kg more heavier than it was before for getting 1 hour extra endurance, right? Now, compare that with batteries. Battery state of the art is 200 watt hour per kg or 0.2 kilowatt hour per kg. And even if I use a state of the art battery, which I will not use because it's not safe on board, there are thermal runaways and other things to consider, I will have to increase the battery weight by 200 kgs. And this is really the contrast between storing hydrogen with fuel cell versus storing battery. Of course, if I go to the low end, then that battery becomes more attractive because I don't need a separate fuel cell, right? Fuel cell is additional weight, which I'm not showing here, right? So that fuel cell weight does not increase when I increase the flight time. Because why? Because it's only converting chemical to electrical. It is not giving you more power than before, right? So it's just like engine, right? My Maruti engine remains 800 cc. I just have a bigger petrol tank, right? So that's what I'm doing. Now, what we did was we designed it with a 60 kilowatt gross fuel cell, and we hybridized it with with about a 5 kilowatt hour battery, and with 2.9 kg of hydrogen being carried in about 42 kg cylinder. Total weight with electric motors, everything included, was we were able to design it in 123 kgs, and the cruise time that we had were 1.23 hours. So this this is what we were able to achieve. And we obviously need higher, and that is where we are headed right now. We are doing a number of system engineering and optimization things to actually improve this much beyond this 1.23 hours that we have achieved. And this is something that not only weight, but we also have to fit the volume, etc., in bigger aircraft, and we were able to fit it within the available volume, within the available kind of structure of the airplane. But of course, going forward, if fuel cells become mainstream, then the aircraft will be designed keeping the fuel cell in mind, rather than trying to retrofit an available aircraft with fuel cell system. But anyway, we were able to fit it, and this is how the fuel cell system looks like. Now, what is it, if you ask, how does this fuel cell look like, how does it function, etc.? We talked about that, right? But what are its characteristics, right? Now, as with any other energy producing device, there are two characteristics. There are two important measurements. One is the voltage and the other is the current, right? Now, voltage multiplied by current is power, and that is what we need, right, from the energy conversion device. Now, what I have done here is to eliminate sort of big fuel cell versus small fuel cell in size, right? So this area, I told you about the membrane, right? So membrane can be small membrane, about 5 centimeter by 5 centimeter. It also can be 20 centimeter by 20 centimeter. How do you compare the two, right? So you compare it on a per unit area basis, right? So when you compare it on a per unit area basis, you get not current, but something called current density, which is basically amperes per meter square or milliamps per centimeter square, as the industry standard is industry language people use. Instead of amperes meter square, you use milliamps per centimeter square, right? Now, voltage is on the y-axis and current is on the x-axis. So if you look at the green curve here, right? So when I'm not drawing any current, right, when my current density is 0, what does that means? That my circuit is open, right? I have an open circuit. I have a very, very high voltage, right? This voltage can be as high as 1.2 volts, right? And as I start drawing more and more current, my voltage drops. And this again has to do with thermodynamics. It can go into it if required, but not pertaining to this lecture. So the voltage drops, right? And but the product of V and I still goes up until a certain point when even the product starts to drop. So that is power, right? So if you look at voltage, you look at the left axis, y-axis, and if you look at the power, you look at the right y-axis, the right side. So that is power, that is watt per centimeter square, and this is voltage. Voltage is voltage, right? And on the x-axis, you have current density in terms of milliamps per centimeter square or ampere per centimeter square, right? So let's compare 2 points in which I can operate the same fuel cell. Let's say I have a fuel cell. I have a choice. I can operate at point A. I can also operate at point B. And I can also operate at a number of other points. I'm just comparing A and B just as an example, right? Now, if I operate at point B, I get higher power for the same area, right? So if you see here, I get a higher power, correct? So now contrast this, I can also operate this at point A, right? In which case I get a higher voltage, but I get a lower power, right? Now, what happens is that I can show it to you in equations, but I don't want to get it into it now. The voltage in a fuel cell is directly proportional to the energy conversion efficiency. That is the chemical to hydrogen energy conversion efficiency, right? And Samartha Kashyap has a question. I'll come to it. That's a very good question. I'll come to it in a second, right? So voltage is directly proportional to fuel cell efficiency. That is what I have shown here, right? And current is basically the number of cells multiplied by the current density multiplied the area of each cell. And you stack number of these together, you make a fuel cell stack, right? Because you can't do much with 1.2 volts. So you stack it up just like you stack up battery, you make a battery pack out of battery cells. Similarly, you make a fuel cell stack out of fuel cell, right? So you stack it up and make it for 48 volts or 50 volts or whatever it is that you want. And you make up a stack, right? So that's the total current in the stack is the total number of cells multiplied by the current density multiplied by the area of the cell, right? And consumption of hydrogen is directly proportional to this current. And so the higher the current, the higher is the energy consumption of the, hydrogen consumption. So I can design the stack, right? I can design the stack for B, right? Let's say I want a 5 kilowatt stack. I can design it keeping in mind that if I'm drawing 5 kilowatt, then I will be operating at point B, right? But most of the time I'm not drawing 5 kilowatt because I'm cruising, and so the cruise power is less, and so I'm drawing maybe 3 kilowatt, 4 kilowatt. When I do that, then I actually operate, although I designed for point B, I'm actually operating at point A. Now this point A is at a higher voltage compared to B, and so therefore it's actually a better efficiency than what is the design efficiency. So this is the primary advantage of a fuel cell versus other types of energy conversion devices such as internal combustion engines. Internal combustion engines, you design it for a certain power. If you operate at less than that power, you are actually less efficient because of the characteristic of that particular device. Whereas the characteristic of this device is like this, right? So what I need to do if I'm designing this system, I need to oversize the fuel cell. I need to have a bigger fuel cell than what I need in terms of nominal power. Why? Because once I have a bigger fuel cell but operate at a partial load, then I get higher voltage, and so therefore I get better efficiency, right? Now you might say, why am I carrying a bigger fuel cell? Because that means also extra weight. Yes, but then I will consume for the same kilowatt hour that I need, I'll consume less hydrogen, or in other words, for the same hydrogen content, I can go long. So there's a trade-off. I need to make that trade-off. I need to identify what that trade-off is, right? So these are system engineering challenges that come up because of the characteristic of the fuel cell. Now, somebody had a question, can we put other kinds of fuel cells? Not able to see that.
It will be in your chat box actually. Yes, you can click on chat.
Yeah.
I think it's sent to you directly, so I cannot see it either.
Oh, okay.
Bottom there is chat. So in your menu, this Zoom menu, you can see the chat.
Okay, I think I have to stop sharing for me to see it. Yeah, can we put other fuel cells for this usage? So which usage did you have in mind? Aviation? Samarth?
Yes, sir.
Yeah, so which kind of fuel cell did you have in mind?
Like solid oxide or proton exchange membrane, yeah, something like that.
Right. So proton exchange membrane and polymer electrolyte membrane are basically the same thing. They are both abbreviated as PEM. So that's the most common thing that people would use. But there are certain situations where you would use a solid oxide fuel cell. And I'll go into when you would do that. So when you would do that is when you have really small aviation devices such as UAVs or drones, etc. Sometimes the solid oxide fuel cell is advantageous because you can use fuels such as LPG and such as liquid fuels such as methanol or ethanol, right? So you can pass that methanol or ethanol or LPG over a catalyst with deficient amount of hydrogen and oxygen, and you can make what is called syngas. You can make hydrogen and carbon monoxide mixture, and this hydrogen and carbon monoxide mixture can then be sent to something called a SOFC. That is what you were alluding to, right? And this SOFC, solid oxide fuel cell, can work and to oxidize this fuel to water and CO2 on board and produce electricity. It works slightly differently than the PEM, but it can be done. And sometimes this is advantageous to do. This system is not very efficient, but there are some constraints sometimes on systems where you want longer endurance, you want very lightweight, but you really don't worry about efficiency. And these are situations where you would use solid oxide fuel cells. So a very good question. And yes, we would like to use SOFCs in certain situations, along with fuel that is not pure hydrogen, because whenever the primary advantage of using what is called a solid oxide fuel cell is that you don't need pure hydrogen, which means you also don't face the difficulties that you face while storing hydrogen and buying the hydrogen and obtaining the hydrogen. You can store and transport fuels that you can store and transport easily, just like I said, methanol, ethanol, LPG, all of these things. And you can convert it to hydrogen on board. Of course, that hydrogen will not be pure. It will have carbon monoxide in it. And if you have a fuel cell that can handle it, PEM certainly cannot, but SOFC can. And so therefore you would use that. Did I answer your question? H2 storage is only available at 6 weight percent. Why not use liquid H2? Yeah, very good question. I can use liquid H2 as well in two situations. One is I can use liquid H2 for really large planes. I can use that because it has a much higher weight percent hydrogen storage than the compressed hydrogen storage. So yes, you're right that we can use cryogenic hydrogen. Now, but the sure, that's very nice. You are working on SOFC as an auxiliary power unit. Where are you from?
Bangalore, sir.
Yeah, where in Bangalore?
Sir, I'm a student at RV College of Engineering.
And where are you sourcing the SOFC from?
Still not yet. It's in the preliminary stages of the sizing and all. So still have a long road ahead. So just ask you for the.
Wonderful, very nice. We can connect later offline. Yeah.
Sure, sir.
Very nice. Yeah.
Love that.
So the question was, why don't you use liquid hydrogen? I can use liquid hydrogen if two situations. Again, in very small vehicles where I don't have an active cooling, right? It's just that I have liquid hydrogen. I charge it into a DVAR which is insulated, but it's still gaining heat from outside, and I let it go. So what happens is a lot of the hydrogen evaporates. Even if I don't need it, I get that hydrogen and I have to vent it. That's okay if I have that kind of mission in mind, right? The other situation where I can use liquid hydrogen, where I have an active cooling mechanism that keeps the hydrogen cold, and that is in very large airplanes. So when you go to very large airplanes, again, you don't go with compressed hydrogen. You go with cryogenic hydrogen, where you keep the hydrogen cold and you take out as much hydrogen as you want only. And that has much higher weight percent than 6% that I mentioned for compressed hydrogen. So again, depending on the situation, size, cruise requirements, requirement of endurance, you choose the particular energy conversion technology, whether you have SOFC or PEMFC, or the energy storage technology, which is compressed hydrogen, metal hydride, chemical storage, hydrocarbons, liquid hydrogen, whatever, right? So does that answer your question? Somebody asked the question.
Yes, sir, it's me. It did answer your question, my question.
Okay,
Thank you.
Vishnu. Yeah,
Yes,
good
sir.
question. Thank you.
Sir, if I follow up on something different.
Yes.
You mentioned, right, because H2 and O2 reaction, this reaction follows first order kinetics, if I'm not wrong. The concentration depends, decides the rate of reaction.
Yeah.
And so the power output.
Correct.
So is this principle used for throttling? I mean, like as a whole aircraft, if I want to throttle is this where we are manipulating, or we are just changing the power at the battery, or we are not
We are
manipulating at electrical level?
at the electrical level. So I would manipulate it at an electrical level, but I also will, what I will do is I will reduce the flow of hydrogen and the oxygen, right? Ultimately. So what I will do in practically what happens is, supposing this fuel cell is connected to a load, right? So once the load starts drawing less power, what happens is the fuel cell voltage goes up, right? When the fuel cell voltage goes up, I will keep on monitoring the fuel cell voltage. And when that goes up, I will automatically reduce the flow of the reactants, which is the hydrogen and the oxygen. That's the control system, right? And when I do that, automatically what will happen is it will adjust so that the power generated and the power consumed are the same. Okay. Of course, there is a middle something power electronics between the fuel cell and the load, that's called a DC to DC converter. I will not go into too much detail, but that DC to DC converter does exactly this same function. Okay.
Okay, sir. Thank you.
All right. So let's look at it in a slightly different way. What are the system requirements? Abhishek, I only have 5 to 10 minutes, correct?
Yes, yes. I mean, if you can wrap it in like 5 to 10 minutes.
All right. I'll wrap it up. So what are the system requirements? What are the difficulties that we run into when we have fuel cell, when we have hydrogen, oxygen, all of these things? So it's not all rosy picture, right? There are difficulties, challenges as well, and we need to manage that. The hydrogen and oxygen cannot be supplied as dry hydrogen and oxygen. Some of these fuel cells require something called humidification, and that is a challenge. So we need to manage the water. Water is also a byproduct, but water also needs to be in the incoming feed. And so there's humidity exchangers that are installed, which further increase the weight and the volume. So that is something that we need to work with. And the cathode side typically is harder than the anode side, which is the hydrogen side. So hydrogen splitting into H plus and electrons is easy, whereas oxygen splitting and adding 2 electrons to oxygen is more difficult. It's called the oxygen reduction reaction. And therefore, we need to maintain a high concentration of oxygen on the cathode side. And when we need to do that, then typically we use compressors or fans or blowers, and that further adds to the weight and the volume, right? And of course, the whole thing, this thermal management is very, very key to the entire system. And so on ground, the situations are very much under control, but in aviation, we need to take care of a lot of other things which are changing with time, and which need to be far more reliable than anything on the ground, right? So this is how the system looks like. Not go into too much detail. Now, you might say, why will this, why would you want to construct such a complicated system for such a small vehicle? It still works out to be much better than batteries, right? Number one. Number two, this is the system as it looks today in a very simplistic manner. And I can try to engineer the system such that a lot of these components are taken out. That will take a hit on efficiency, that will take a hit on endurance, but I will need to make a trade-off, which is why I need to study this system and say, okay, what is optimum for my particular application? That is what we do at our lab, right? And so this is a list of components, but this is how we fit it into the cowl of the aircraft, right? So this is now a design that is now, actually we're, getting to implement this design. But this is where we designed, there was a fuel cell stack, there's thermal management, there's hydrogen storage, everything inside the cowl where the engine used to be before, right? And you can still see there are holes for the propeller to come out, and there's a fan that comes out of the propeller blade that comes out, that projects out, right? So again, some very preliminary observations, right? So typically the thought process is that if you have 1 kg of takeoff weight, you need 200 to 300 watt takeoff power, right? So that means 200 to 300 watt of power for every kg of takeoff weight is required. Now, can batteries meet this? Of course they can meet this. But what they cannot meet is endurance, how long you go, how long you fly, right? And that is where fuel cell systems are far better than batteries. So batteries are about 200 to 300 watt hour per kg, whereas fuel cell systems can be 800 to 1000 watt hour per kg. That is 3 to 4 times better, right? So if you have a short endurance mission, or if you have a very short endurance flight requirement, then you perhaps are better off with battery, especially the smaller ones, right? When you have larger vehicles and when you have longer endurance requirements, You cannot do batteries. And that is what I'm trying to get at. And but sometimes you hybridize. So instead of carrying a very high fuel cell, a very high capacity fuel cell, I'll carry a smaller fuel cell, but I will also carry a super capacitor or a battery. And that I will use only when takeoff and landing. And during cruise, I will use the fuel cell mode, right? So these are options that are available to a system designer. And we every day wrestle with these options and try to see which one is better. So again, for a 10 kilowatt, if you have a 10 kilowatt drone, right, you need 9 kg extra for every 1 hour of flight for a fuel cell system. For state-of-the-art batteries, you need 33 kg extra, right? And that's the comparison we're talking about. So if I put this on a graph, like this is what I want to leave you with. So if I plot energy density, that is watt hour per kg on the x-axis, and power density on the y-axis. I'm not talking about individual devices. I'm talking about a 10 kilowatt drone that is flying only for half an hour on the left side, whereas something that is flying for 4 hours on the right side. So somebody asked, where is LPG plus SOFC, right? So that's where you can see it on the graph, LPG plus SOFC, right? And where is cryogenic hydrogen? It's very, very much higher. Okay. Now, that being said, can I use cryogenic hydrogen today? No, the answer is no. Simply because cryogenic hydrogen is not available. The devices need to make cryogenic hydrogen are not universally available. The DORs and the storage containers needed to keep hydrogen in cryogenic state are not easily available. They are very expensive. And so, but we can get there, right? So if I use cryogenic hydrogen, if you see the left graph, it's all muddled up. They are more or less the same. But if you see the right graph where I'm having 4 hours of endurance, you can see battery is performing the worst because of the same reason that battery, if you want to increase energy, you got to increase the power. You got to increase the entire battery. There's no other option. Whereas if I want to increase the endurance in a fuel cell system, I will try to increase the hydrogen that I can. I don't need to do anything to the rest of the system or to the fuel cell, right? And that is where the real value opens up, because then you see the real value. You get that 300 watt per kg with cryogenic hydrogen, with compressed hydrogen, and some of the configurations that we can use with PEMFC, which are more commonly available. Compressed hydrogen is more commonly available, right? So we want to travel that path, right? And that is what we are trying to do. So I'll stop here and I will leave you with questions that perhaps you will have. I just wanted to show you one alternate configuration. We can carry hydrogen in multiple forms, I said. So sodium borohydride is one of those forms. Sodium borohydride, if I mix it with steam, if I have a steam generator and I mix it with steam, I can generate hydrogen. So sodium borohydride, when it reacts with water, you get hydrogen and you get certain byproducts which you don't use, but that hydrogen can then go to a stack. So again, I have reduced the weight of hydrogen carriage. So this is another option that I have. Similarly, there is aluminum hydrides. There are other kinds of hydrogen storage that I can use depending on, again, it's specific to the application. If I have certain kind of application, depending on the power profile, depending on the endurance, depending on the power requirement, I'll use certain options. So, but I'll stop here, and I will, I've already overshot my time, and the next speaker might be waiting. So I'll stop here and take any questions if there are any quick questions.
Sir, I had a question.
Yes.
In the context of drones and UAVs, where we have constraints related to weight and size and all,
Right.
and we have a heavy payload system which consumes almost 40 kilowatts of power, how
Right.
commercially feasible and viable it is at this stage to power the whole system using hydrogen fuel cell technology?
What is the endurance requirement?
Somewhere around 1.5 hours. So I'm coming, I'll just give you a background. So I've reached out to a company called Intelligent Energy, who's making something very similar. And they have maximum 2.5 or 2.4 kilowatt of fuel cells, which according to me commercially is not very viable, though it appeals for a very good cause in the long run. But in the Indian context, where we have a very price sensitive market, do you feel that we have still reached a stage where something like this can be implemented commercially, or we are still at a nascent stage?
Yeah, I think commercially, the question is, what is the cost target?
So I'm basically looking in terms of endurance, where the existing battery system, the battery system has a lot of limitations. You need to charge it to bring the drone back. You need to set up some infrastructure. Plus,
Right.
you don't get the kind of endurance which fuel cell gives. There is no doubt about it. But
Right.
we are very keen to implement something like this. So
Right.
are we still, have we reached that place in the Indian context where we can do something like this?
That's a difficult question to answer for the simple reason that we have to start with what is the cost per kilowatt, let's say, or the system cost, right?
Yeah.
So if we can start from there, then we can figure out whether we are there or not, right?
Yeah.
In some applications, the cost tolerance or the capital cost tolerance is higher.
Okay.
Especially in military and other applications, but maybe you are hinting at commercial applications.
Correct.
Again, in some commercial applications, I can tolerate a higher cost if my operating cost goes down.
Okay.
And in some applications, I cannot. So my suggestion is that we can connect offline and discuss what is possible versus what is not possible today, right?
Okay.
Yeah.
So, but what intelligent energy is doing is some in the similar context. Have they reached that point? I don't know much about them.
Yeah, we can discuss that. I don't want to
So
discuss.
this intelligent energy, if I can intervene, is that the company from UK, right?
Correct, sir. Correct, sir.
Yeah. So they actually had participated in this competition organized by NIST in US, where we also were actually competing with them.
Okay.
So they, I believe, were second in that competition, where they flew a hexacopter, big hexacopter with 5 kilogram payload for, I think, 80 odd minutes, something like that.
Okay.
But same thing we could actually reach with the fuel, I mean, normal conventional with a gasoline engine based system as well.
Okay.
At a much lower weight, because like what Professor Atul has just mentioned, that when you go to higher power, then I mean this overall weight of the system and other things actually, I mean, beyond a point, because this was actually still a system which only required, I mean, 2 to 3 kilowatt of power probably. Okay. So that's where, I mean, they could, whatever they could do, I mean, it was also achievable from conventional gasoline based system as well. But yes,
So
battery was.
What I understand, sir, from your inputs is that if the system is really big and you're looking for long endurance, long cargo kind of a system, that's where this will actually be viable to justify the weight and the cost of the whole system. Am I correct, sir?
Yes, but what I want to also say is that its weight is actually less than an equivalent battery operated drone or vehicle. You cannot, beyond a certain endurance, you cannot do it with battery. You just have no option.
Correct. Okay. That helps, sir. Thank you so much.
Yeah, and we can touch base offline. So you're from where? Which?
Sir, we are a startup based out of Mumbai. My name is Dhaval. The company's name is Blue Infinity. We did a couple of UAV projects, but the battery-based system, as you know, has a lot of limitations and all.
Right.
So fuel cell is something that looks to be quite promising.
Initially, these are systems that will be attractive to the strategic applications because they have an added advantage that they are very silent. Whereas if you have an internal combustion engine like a petrol engine or something like that,
Correct.
that noise signature and heat signature is something that will give it away.
Yes.
And so that is an additional advantage, and therefore the initial applications might be in strategic applications.
Also, sir, IC engine is prone to more maintenance comparatively.
Yeah, smaller ones, yes, true to a certain extent, yes.
Okay, thank you for your answer.
Yeah.
So I think we are already, I mean, we have overshot the time, so we'll stop here now. I mean, if you have further questions, I'll request Dr. Professor Atul Bhargav to stay back a little bit and maybe answer some questions, I mean, through chat if anybody else has. So you can send questions on the chat box and he may be able to answer that. So now we'll
just, sorry, I'll just type out my email address.
Right, that will be great. Actually, you can
I just typed it out in the chat box, and
so anybody has any further questions, you can directly connect with Professor Atul Bhargav. His phone number and email address is already available. So thank you so much for this very insightful and really exciting talk, and great learning experience for me as well. Because we look to work together on this, I mean, in future, and take things forward from there as well.
Yeah.
So with that, I mean, I'll share my screen and I'll invite our next speaker. So we have the final talk of this event that is going to be given by Professor Jayant Sirohi. So Professor Jayant Sirohi is a professor of aerospace engineering at the Cockrell School of Engineering at University of Texas at Austin. He has been involved with conceptual design of, so before that actually he had worked at Otto Sikorsky Aircraft and he did his PhD and postdoctoral research at University of Maryland. At UT Austin, he works on projects related to smart material sensors, experimental aerodynamics and structural dynamics, also energy harvesting and rotary wing aeroelasticity. He has been principal investigator of this VLR COE funded by US Army, Navy and NASA. So with this brief introduction, I'll request Professor Sirohi to share his screen and start the talk. And thank you also for joining earlier and participating in the previous presentation also.
Thank you, Professor Abhishek, for the introduction. I did enjoy the previous talk also. It's a good learning experience for me as well. Okay, can everyone see?
Yes.
See the screen? Yeah.
Yes.
In the slideshow mode? Okay.
Right now we are seeing it actually in the presenters mode.
Oh. Now?
Yeah. Now
Okay.
it's fine.
So thank you for inviting me to give this presentation. I will start with a brief description or introduction to where we are or who we are, and then go into the topic. And just like the previous presenter said, feel free to stop me and ask any questions whenever you have. So I'm a professor in the aerospace department at UT Austin, and this is where we are located at Austin, Texas. The University of Texas at Austin is in the capital city of Texas. That's a picture of our campus here. It's a very large university, about 50,000 students, and we are specifically in the Cockrell School of Engineering. We have about 500 undergraduate students, 165 graduate students, and we're ranked in the top 10. Usually, Texas A&M and UT Austin, have a friendly competition as to who is better ranked in the top 10. So, a lot of PhD students, and so if anyone is looking for graduate school opportunities, you should definitely consider UT Austin. In UT Austin, this is the research group that I have, vertical lift research. And we have these areas of expertise: experimental aeromechanics for the rotary wing, conceptual design, aeroelasticity. Today, I'll specifically be talking about this auto-rotating payload delivery system. But first, I just wanted to show the different types of facilities we have in our group. Here's a picture of a test stand that we designed and built, coaxial counter-rotating test stand. We happen to put this in the University of Maryland wind tunnel, so you can see the Terrapin logo there for, Professor Atul can maybe recognize this here. Then we also have another coaxial test stand, which we have with a horizontal shaft. And the reason for that is we do a lot of optical diagnostics on these rotors. So here's an example. We have the rotor mounted in a horizontal configuration, and this is a fully instrumented rotor. It has a swash plate. The hub can be articulated or rigid hub. In this particular case, it's a 2-meter diameter coaxial test stand. The blades are painted in this fluorescent orange, you can see, with some pattern of dots on them. And the reason for that is we use it to measure the blade deformation. As the rotor is spinning, we can illuminate it with some lasers and then take the images with camera, high-speed video. And with the high-speed video, we are able to extract the blade deformation. You see that here You see that here in this picture. This is a composite image of the rotor disc strobed at 32 per revolution. As the blade goes around, you can capture the blade and extract the deformation as a function of time. And from there, you can do various things like modal analysis. You can calculate the rotor blade frequencies, mode shapes, and so on. So that's the rotor blade deformation using digital image correlation. We also can measure the rotor wake using PIV, that's particle image velocimetry. Here's a snapshot. The rotor is, again, sideways. This is a rotor blade. We illuminate the rotor with a laser sheet, and we apply some fog particles in the flow field. And by tracking the fog as it moves through the laser sheet, we are able to measure the flow velocity through the rotor. We also are doing some work in acoustics. We have an outdoor test facility here. This is a picture of the rotor, and we have some microphones in an arc around the rotor. And here is the actual picture of the system with those white things on the ground. Those are the microphones. So this is a video. Let me see if I can play it. I have many videos in my lecture. Right, so that's a full, the full test matrix will involve many different operating conditions. And the 2-meter diameter rotor can absorb maybe something like 12 or 15 kilowatts. That's the range of power that we're talking about. Okay, so coming to the topic of today, I'm talking about aerial payload delivery. So if you want to deliver a payload from an airplane to a point on the ground, typically the way it's done today is parachutes. So here's a picture of many parachutes and people hanging from the parachutes. And that's a very reliable way of doing it. It's been done like that for a long time, except it is very susceptible to wind. So the accuracy is affected by the wind. For example, here is a calculation of the trajectory followed by a 10-centimeter ball, just a sphere, if it's dropped from a height of 50 meters. And you're looking at it in 5 miles per hour mean wind with some random variations. You can see that the trajectory is very significantly affected by the wind. And this is just a small ball. So imagine if you have a large parachute and a payload hanging from it, it can definitely be diverted considerably far from where its intended landing zone is. So not only does it get diverted, but there is also a very large spread in the possible landing zones due to the stochastic nature of the wind. So how do we make this a better or more accurate drop for the payload? Now, this is probably not so important if you are dropping in a big field like this, like you see in this picture, but for any kind of payload where you want it to drop at a very specific, precise point, like for example, you are giving some emergency supplies to some people who are floating in a boat in the sea. You need it to fall in the boat, right? You don't want the payload to fall in the sea and then it'll be useless. You don't want the supplies to be lost in that way. Or if you're doing the delivery of packages, nowadays you get packages delivered home by Amazon or whoever. But imagine that you can save a lot of time by just dropping it from the sky, and it somehow reaches you, but accurately. You don't want it to go and fall in the neighbor's house, but you want to fall right in your house. So how do we steer this package in a more accurate way? So one way we're looking at is using an auto-rotational decelerator. So here's a picture of a maple seed. And so this is an auto-rotational decelerator that's found in nature. It falls from the tree. There's a seed here. And as it falls, it rotates. It's basically a helicopter rotor operating in auto-rotation. And the state of auto-rotation is such that there's an energy balance between potential energy, rate of change of potential energy as the rotor is dropping, and the kinetic energy of the rotor itself. So these kind of decelerators are found in nature, and they're also been developed for, into many applications in the past. For example, the Cayman rotor chute, as you see here. This is a person who's holding the rotor chute, different scales. You can see a very large one and a very small one that he has in his hand. So it can be made over a very large range of scales. What are the advantages of this thing? Firstly, you can have greater control over the loads as compared to a parachute, because it's essentially a helicopter rotor. And when you look at a helicopter rotor, you can apply then to its cyclic and collective pitch control. If by doing cyclic pitch control, you can steer the rotor to any sideways direction. You can make it essentially do a glide and increase the range of the travel as it descends and so on. So it is basically like a helicopter rotor that you're trying to control as it's descending. So that's a possibility of guided flight with the cyclic control. Another important advantage, which is not so obvious, is that when you have a parachute, as soon as the parachute opens, there's something called opening shock. There's a very large jerk on the parachute cables as soon as the parachute inflates and opens. But in the case of a rotor that's entering into auto rotation, It's a very gentle decelerating force with time. So there is no opening shock as such. So those are the advantages. And so this is the kind of concept we want. We have an airplane or a helicopter, we drop this package, and there's a wind profile and there's a target that we reach. And here is, we want an autonomous steerable decelerator that can be deployed from an aircraft and accurately deliver the payload. So here is the prototype, it's the schematic. You have some control mechanism and the rotor, the body and nose cone. The body will hold the payload, and the rotor, we want it to fold up against the body itself so that you can stow it in the aircraft. We don't want this rotor to be sticking out and like open all the time, because that would be very inconvenient in terms of keeping it in the aircraft itself. So you want the rotor blades to fold up against the side of the device like this. This is one of the prototypes we made. This is just a loop of a ribbon to drop it from a drone. And you can see the blades are now folded up nicely against the side of the payload itself. So that's the kind of concept that we are going to go forward with. And the other, one more important thing that I want to note is that it is possible to do all this using some flight control system and a very complicated swash plate that changes the collective pitch and introduces cyclic. But here in this case, we want to make it as passive as possible. Can we make the blades deploy in a completely passive fashion from this stored position where the blades are along the side of the body? Can we make it such that the blades open up, deploy in a very passive fashion? The rotor collective pitch versus time is also controlled in a passive fashion. The only thing active will be the cyclic control, which we can implement in a very simple manner. So further examples of how people did it in the past, this is a picture from 1966. This corporation, Cayman Aircraft Corporation, has been looking at this thing for a long time, even for re-entry vehicles. So for example, instead of using a parachute to slow down a re-entry vehicle and then deliver it, they wanted to use this kind of system where you have rotors that open up. It's such a high altitude. If you look at the plot on the right, rotors are deployed at 100,000 feet. Decelerates the whole aircraft to about 60,000 feet, and then you initiate a glide, which is basically you're putting cyclic control, and you let it go glide down range almost 25 miles to the landing zone. So that's what they proposed. They built many prototypes. Rotors were deployed even at supersonic conditions like Mach 3. But it had to have a very complicated control system in terms of linkages and swash plates and all that. So using technological advances in materials, guidance, control, and so on, we want to re-examine this concept. See, can we make it as simple as possible, but also retain the functionality of having a deceleration, but also a steerable deceleration to a specific location on the ground. That is our motivation. So we built a prototype. The prototype could fit in a 1 inch by 1 inch or 8 inch volume. Here you see the dimensions. And the rotor blades were basically a thin circular arc airfoil so that you can fold them up against the side of the body itself. So this is the picture of the whole system when the rotor blades are stored. And we wanted to make sure that this is very robust. So we made it in this way so that we can shoot it out of a pneumatic gun with a 1 inch by 1 inch barrel. We can shoot it out in any orientation we want and see if the rotor blades deploy passively by themselves in any orientation and if they are survivable. So that's why we made it in this very small form factor, because it's then easier to scale it up and then drop it in more benign conditions. As soon as it is launched, the blades open up like this. Okay, completely passive. They open up purely because of inertial forces and aerodynamic forces acting on the blade and the whole body as it tumbles through the air. Once it opens up like this, the airflow starts interacting with the blades and the rotation starts. As soon as the rotor starts rotating, centrifugal forces on the blade make it go, make them extend outward. And you get this kind of situation here where you have a free stream velocity from below due to the descent of the whole device, and the rotor blades are spinning. And the rotational, because of rotation, the centrifugal forces keeping the blades out, extended out like this. So this is a stable auto rotation condition in which it's descending, and it then can be steered to the location. So this is a prototype to explore the concept of, can the blades be deployed completely passively in any orientation? And can we get the required performance in terms of descent velocity? Okay, let's look at the operating conditions at the airfoil itself. Here we have a cross section of the circular arc airfoil. Right, this dark black thing is a circular arc airfoil, and you have incident velocity. This is the rotational velocity. This is the descent velocity minus the induced inflow. And here's a relative velocity. So that creates a large angle of attack for the blades. Now, the blades are not spinning to begin with, right? They have just deployed, and there is a large incident velocity coming from below because it's falling through the air. Now we need to make the rotor start rotating. And the only way we can do that is to make this incidence angle negative, so that the angle of attack in this way creates a lift vector and a thrust vector that have a resultant along the direction of rotation. So this resultant, that's L sine phi minus D sine phi, has a resultant that's along the direction of rotation in plane accelerating torque that makes the rotor start spinning up. So now the rotor blades have this accelerating torque going to the left, so the rotor spins up and reaches a steady state operating condition. So the conclusion is that we need a negative collective pitch for initiating the rotation in this direction. But once it reaches steady state, if it has a negative pitch, then the thrust that it can produce is not so high. So we need a positive collective pitch to generate high thrust, right? So these are two contradicting requirements. Initially, we need a negative pitch to start the rotor. But if you want to minimize descent velocity, or in other words, maximize the thrust and make it spin up as soon as possible, we want to have a positive collective pitch. So you want to transition from negative to positive pitch. And again, we want to do this in a passive way. So we came up with this articulated hub design. We have a dual hinge here on the right. You can see there's a flap hinge that allows the blades to be stowed against the payload body. And there's a skewed flap hinge outboard of this stowing hinge that has a pitch flap coupling. So after deployment, the blades flap up till this hinge locks, and this hinge is free to flap. Because of the rotation, the flap angle decreases because of centrifugal forces, and now the pitch angle starts increasing again. So the pitch flap coupling is very, very important here, and that's key to determining the time history of the collective pitch angle as a function of descent speed and rotor speed and so on. Right, so I'll show you a video of how this works in a little bit. But first step, this is typical for any kind of air vehicle project. You come up with a design, conceptual design, you make an analysis, then you make a little prototype, do a wind tunnel test, and do a flight test. And then you can compare your analysis with all those measurements and see if you can then scale it up to an actual air vehicle. So that's the same process we followed here. So here is the wind tunnel setup. You have the wind tunnel flow is coming from left to right in this case. The rotor is a fixed pitch rotor. It's just spinning this way. And there's a load cell and an optical switch that determines the rotor speed. So we tried two different types of hubs. First, there's a fixed pitch hub to just find if the relation between the descent velocity, which is in this case the wind tunnel velocity, and the rotor speed and the rotor thrust. And this we can match with our analysis using a simple blade element momentum theory in this case. Then we put in the articulated rotor system, which has the sequence of hinges, and we tried out untwisted and twisted blades and see how they behave. So that's the general process. So here, quick look at the rotor properties. They're about the same rotor radius, about 200 millimeter radius, and about the same chord. The differences occur because of the design of the rotor hubs itself. We tried some linear twist, and we have a delta 3 angle. That's the most important thing here, of minus 30 degrees. And we also limit the flap angle to 45 degrees, because if you allow this thing to flap completely, then it's not going to ever start spinning. It's just going to flap all the way back and drop straight down. So we don't want that to happen. So we limit the flap angle to 45 degrees. And so in that situation, it's going to start rotating in the right direction. So here are some results with a fixed pitch hub. So again, this has no hinges at all. you have a fixed pitch hub. I'm plotting descent velocity here on the x-axis, that's the wind tunnel velocity, and the thrust on the rotor itself. You see different collective pitch angles. So you see here, as you, this should be a negative angle here. It's -2, -6, and -10 degrees. With -10 degrees, you see that there is less thrust, right? But you need the -10 to initiate rotation in the correct directions. But your steady state thrust will be low. As you increase the collective pitch from -10 to -6 and -6 to -2, you get more thrust. So the thrust increases with the pitch angle, whereas the changes in the rotor speed are relatively small. It's around 2000 RPM at 6 meters per second. But the thrust, there's a large variation in the thrust. So this shows that we need a negative angle to start the rotation, but we need an increasing angle to create more thrust. In all these cases, the rotor is operating at a constant tip speed ratio and constant CT in this case. So we also have those solid lines, which are our analysis. And you can see that once we start getting into -2 degrees, you've entered this turbulent wake state. It's very difficult to have a good aerodynamic model for such small pitch angles. Now, more interesting is, how does the rotor spin up to begin with? The rate of change of the rotor speed. So here is 6 meters per second, and we're looking at the thrust and the rotor speed as you start from 0. So initially at 0 time, the rotor is held fixed. We just hold it by hand and let go at time t equals 0 and see how the thrust increases with time. So thrust slowly increases. There's a little bit of overshoot and reaches this steady state condition about 3.5 newtons or so. And the rotor speed starts from 0, again slowly increases and goes to steady state of 2000 RPM. So you see it takes almost 20 seconds for that rotor speed to reach steady state. 20 seconds is a long time. We don't want this thing to keep falling, in almost like free fall for 20 seconds. Now, if you have a more negative collective pitch, you see that these transients occur much faster. So in 4 seconds, you reach steady state. And at -10 degrees, you have much more negative collective pitch, much higher accelerating torque for the rotor. So rotor spins up much faster. In almost about 3 seconds, it reaches a steady state condition here. Right, so that's what happens to fixed pitch hub. So the conclusion then again, as I said, is negative pitch, more negative pitch, faster spin up, which we want, but then we need to increase the collective pitch to positive value, so we get large steady state thrust.
So what are the delta 3 values for these, Dr. Sirohi?
In all these cases, this is fixed. There was no hinge at all, right?
Oh, okay.
Because there was no hinge, you can see that if the collective pitch is -2, it takes 20 seconds. If it's -6, it takes around 3 seconds, and -10, it takes around 2.5 seconds. But there was no hinges in this case. This is only for checking if the analysis matches the experiment.
Okay. Understood.
And you see that we need the with the Peters-Chen model with dynamic inflow, it doesn't match so well, and we have to make some modifications, including large angles, large aerodynamic angles, and so on to match it. So next we'll look at with the articulated hub. We see that as you increase the descent velocity, the thrust doesn't go quadratic anymore, and the rotor speed also has some kind of discrepancy here. In this case, these cases we're using twisted blades, and the blades are very thin. So what we found is that there is a lot of elastic deformation, and that kind of changes the results a lot. But it shows that even with the articulated hub, it's working as we expect. We're getting a good amount of thrust, and we can stabilize it somehow by adding a little bit of a leading edge mass. But let's look at a video here. This is very important. On the left, we have a video of the rotor in the wind tunnel. This is a high-speed video. This is the person's hand holding the rotor. The incident wind is from the right to the left. So it's coming from the right to the left. So the rotor is held in this position, which is somewhat as if it is just released from a stored position. So as the video plays, you will see that okay, so you see that the rotor blades are, I hope you can see the video playing. The rotor blades flap all the way back, they hit the stop, and it starts spinning. Can you see the video?
Yes, it is
Okay.
playing, yes.
Okay, good. So now you see it's spinning, right? So as it's spinning, it started spinning almost instantaneously as it flapped back. And as it's spinning, the rotor speed as the rotor speed increases, centrifugal forces on the rotor blades increase and they extend outwards to reach a steady state. And again, this has, there's a big effect of twisted or untwisted blades, as we know that although for an optimum hovering rotor, you need a negative twist distribution. For good performance in auto rotation, we need a positive twist distribution. So on the right-hand side, you can see that with a twisted case, you have a much higher steady state thrust. Untwisted case, you have a lower steady state thrust. But more importantly, you see that the rotor has started spinning and reached the steady state thrust in just about a second. A very fast spin up. So the pitch flap coupling increases the rotor acceleration, and there's no thrust overshoot. It just smoothly reaches your steady state velocity. So that's the operating principle, right? So with this high speed video or slow motion video, you're able to see exactly how the rotor blade is deployed. Okay, so next we started building a flight test article. So this is to be dropped from a drone or shot out of a pneumatic cannon to make sure that all the rotor deployment works in any kind of orientation of body or any crosswind. So we also instrumented it with a microcontroller to take all the data. There's an altimeter, 9-degree of freedom, IMU, and a Hall sensor to measure rotor speed. All that is enclosed in this little 1 inch by 1 inch square cross section with a battery. Total mass was kept at 150 grams. You can see we added some mass here just to make the mass more realistic, like a payload, right? And we have coordinate system. The z-axis is oriented along the rotor axis, and we use untwisted blades because they're just more stable in this case. So first step, we dropped it from a quadcopter, just modified the quadcopter so it has this payload tube, and it's got a servo and a hatch door that opens whenever we command it. So we can see a video from the quadcopter itself. As the video plays, you'll see it's flying over this ground. It's flying over the ground, and so there you saw it. As soon as it dropped, the rotor blades deployed. And let's see that again. So the door is going to open. There it drops, and the rotor blades immediately deploy, and the rotor starts spinning. And so this was the drop from a drone. It's a very controlled environment. Let's say there's not much crosswind, and the whole payload delivery device was pointed down, which is the best orientation for the rotor to start spinning. So there's not much of a challenge in terms of opening the rotor or deploying the rotor in this case. We know that it's going to deploy. We just want to make sure that the analysis matches with our experiment. So we look at our measurements. On the right, you see some snapshots. As soon as it drops from the drone, one rotor blade is deployed. After a second, the second one comes out, and then 2 seconds and 3 seconds it starts spinning, but there's also some precession and so on. So we perform 3 drop tests from different heights. You can see there's a linear region where it reaches a steady state descent velocity. So it's about 4.8 meters per second in this case. It's comparable to a parachute of the same diameter, right? So it's working exactly like what we intended it. If you look at the accelerometer measurement, we can derive the rotor thrust from the z direction acceleration, along with knowing the whole mass of the device. So here, this is your 1g acting on it. As soon as you drop it, it goes into free fall, about 0g. And then as the rotor starts spinning up and the thrust increases, within less than a second, you reach a steady state value. The thrust is equal to weight at that point, and it's reaching steady state descent in this condition. Another interesting thing is if you look at the magnetometer reading around the z-axis, there is an oscillation, right? There is the oscillation that reveals there's a body orientation changing. And there's not only spinning of the body, but there's also some precession and nutation going on. And that's because although the rotor is spinning and supported by two bearings, there's a very small friction in those bearings. And so after some time, there is some small torque that's transmitted to the rotor body itself, from the rotor to the body itself. It makes the body start spinning. So there, the body itself is spinning, it's dropping, and so the whole thing acts like a gyro, and there's some precession and nutation. So this is something we need to address. How do you minimize the body rotation or cancel it in some way, right? So it gives you a large amount of body rotation, which you can see here in the green and the blue. Okay. So next step was to try to launch it from any orientation. So the goal is, can this thing deploy its blades and be survivable, even if there's a crosswind or if it's somehow dropped in the wrong orientation or something? Because we don't want it to be exactly dropped actually down all the time. That's just not feasible in real life. So we put the whole thing into this pneumatic cannon, as you can see here on the right. It is essentially an aluminum tube. That's a square tube, and you can charge it up with air, 50 psi or so, and then just open it up, and it will shoot it out at approximately 27 meters per second. So this could be another way of deploying the payload from an airplane itself. So we looked at two different launch orientations. Either shooting it out with the rotor first, or shooting it out with the bottom of it first, which is, we call it head first or tail first. And the tail first means as soon as it's launched from the cannon, it sees a very large dynamic pressure that's making the blades open up. So that would be a very extreme condition where you want to test if the blades are strong enough and the deployment is as we expect. Then we also shoot it head first, which means the rotor hub is first. Here is totally opposite condition, because the dynamic pressure due to the launch velocity wants to make the rotor blades stay in the stored position. So it doesn't really want to deploy at all. But what will happen is, after it launches from the barrel, there'll be some tumbling motion, three-dimensional motion that will be introduced because the offset brings CG in the center of pressure and so on. And as it tumbles, there will be some air that will basically be incident on the rotor blades from below. And at some point, it's going to start spinning. So the question is, how long does it take to initiate rotation, even in the worst possible case, where you have a head first launch? Right? So if you see in the nature, all these maple seeds, right, they have a seed on one end, and they have this rotor blade, really, which is like the membrane on the other end. So the way they're on the tree itself is such that the seed is upward and the blade is pointing downward. So when it drops, it's always going to enter into the autorotation. And there's only one geometry where this maple seed will not enter autorotation, and that's where the seed is pointing exactly downwards. So if you hold it by the membrane such that the seed is exactly downwards and you drop it, it'll fall straight down. It's not going to start spinning. But it's very interesting that in nature, it's held in exactly the opposite position, right? So that that orientation in which it doesn't start spinning is not a factor. So we want to make sure it spins in any orientation here. So the first video that I'll show is it's launched. This is launched from the gun, and it's a tail first deployment. So you have immediate deployment of the rotor blades as soon as it reaches its launch velocity and leaves the barrel of this cannon. So we have this video here to the right. So it launches, blades deploy immediately, it's spinning immediately. And as it falls, it's entering auto rotation there. So this is the worst case scenario for blade strength. Right, so let me play this again. Then it launches, blades open up immediately and start spinning. So if the blades are able to survive this kind of launch, then they should be able to survive any kind of orientation, launch orientation. So you can see we have a high-speed camera looking at it from the side, and you can see that using a high-speed camera and photogrammetry, you can see that it's approximately 50 meters per second squared in terms of deceleration produced by the opening of the rotor. So here's a side view of it. You see on the right-hand side, down here, that's the barrel of the pneumatic cannon. And as it plays, this slow motion video plays, you'll see the projectile coming out from the barrel, and the blades will open up and it'll deploy. So there it comes. and the blades open up very soon, and the rotation starts. So here, very interesting thing is, since the blades have been made very flexible, that actually helps them survive the launch. So the launch loads are very high, but the blades, since they're flexible, they in fact, if you look at a close-up of this video, the blades fold all the way back, and since they're so flexible, they almost cross. They cross here, but still they haven't broken, because the flexibility of the blades allows them to withstand this kind of dynamic pressures. Then the blades open up again, and as you see this composite image, the rotor starts spinning, centrifugal flow forces pushes the blade out, and it reaches the stable condition. So now there's a very large drag on the rotor here. Center of gravity is up here, so it's going to stabilize itself and enter a steady descent on the other end of this drop. Okay, then we did a head first launch. This is just a composite video, composite image from the video. As soon as it leaves the barrel of the cannon, the blades are still stored against the body of this device for a long time, because the dynamic pressure is keeping the blades stored, right? So it reaches the top of this trajectory and it starts tumbling. As soon as it starts tumbling, there is some incident velocity from the bottom of the rotor blades. So then the blades open up, and over here you can see that it's entering into the stable auto rotation here. So the deployment here stabilizes the payload, and you can reconstruct the trajectory. If you look at the X and Y positions here and height on the Y and the Z axis. So this is the launch. It goes straight up because the blades are still stored, and starts tumbling here. Blades deploy. And as soon as the blades deploy, it enters stable auto rotation, and just the prevailing wind brings it to a sidewards glide here. So this whole portion here, from about this 20 meters downrange all the way to 40 meters, is all in auto rotation. Right. So those are the results of the launch test. So at this point, I'll just conclude. We designed this autorotative payload system and tested it. We demonstrated steady state descent characteristics similar to a parachute. And we showed that the blades are not only strong enough to withstand severe launch conditions, but also they'll reliably enter the auto rotation from almost any orientation. So that's very, very important in terms of payload delivery. Although we're not going to shoot it out of a cannon like that. There could be a large crosswind when you deploy it from an airplane. And so it's important that it stabilizes and deploys as soon as possible. We also validated these analytical models against these wind tunnel tests and the drop tests. And so now that we have the model, what we can do is explore how this thing can be scaled up to larger payloads. Can it, so this one was basically 200 grams, 150 grams all up weight. So can we make it carry a 1 kilogram payload? Can we make it carry 10 kilograms or 50? You can explore that kind of scaling by doing just a simple conceptual design study and using this validated analysis. So that's all I had to present today. If there's any other questions, I can be happy to answer them.
So in this, so I have a question before we go to the audience. So
okay.
In these experiments, you always see it towards end starts processing, or it's only happens once in a while?
The processing will always happen in this case, because when you look at let me show you back here. Okay, like even here, you see, the rotor is now a very large source of drag, right? And the CG is below it, but it becomes an unstable system. Mm-hmm. And so there's a pitching moment on the whole body, that's a destabilizing pitching moment. So that's what causes the precession. So eventually what it's very important to have a tail on this thing, and the tail stabilizes it. So I have a little video here at the end. We just did a drop test from another drone. Up here in the top up here, there's a drone that can carry a large payload, like 10 kilogram payload. And we're taking video from a small drone that's flying around and looking at it. So the small drone will fly up there. This big drone here is carrying one of our larger prototypes, which is about all up weight of about about half a kilogram. And you can see that that has a tail. So as you drop it, it doesn't undergo any kind of precession and so on. You'll see the video here. So we're flying up towards the other drone. You can see our prototype hanging from below. It's hanging from below. Now it's dropped, deploys. Initially, there is some precession, but now it's stabilized. See, as it comes down, it's stabilized. There. And the stabilized because it has a tail. The tail has to be above the rotor plane. And you have to design it so that the stability is guaranteed.
And another follow-up question is, so right now it is only having a fixed pitch setup there, or you have a collective pitch change or something like that?
There's no collective, it's still all fixed pitch, but there is in this prototype, which you just showed the video here, it is a collective, there's no collective pitch, but there is a cyclic pitch.
Oh, there is a cyclic.
It's a two-bladed rotor, and you can do cyclic pitch to control the sideways forces, but no collective pitch. The collective pitch is all completely passive. Deployment of the blades and this pitch sequencing is all passive. And that's just to minimize complexity and minimize. But again, that can be, you can argue that why do we need to do that? You can just have a regular swash plate and program in the collective pitch. That way, when just before it lands, you can do a flare also.
Right.
And minimize the descent velocity
yeah.
further. Yeah. So basically, you can make an exact replica of a helicopter with swash plate and all that, with the proper flight control laws. Only difference will be the deployment. You just have to make sure that the blades deploy. You still need the skewed hinge so that it deploys and starts initiating rotation in the correct direction. And after that, everything else can be swash plate. So this is something easy for you. You can do it in your lab quite easily, I'm sure.
Actually, we had done that already. I mean, we had presented that in VFS also.
I see. The boomerang, I remember the robotic boomerang, right?
No, not that one actually. For the normal helicopter, conventional helicopter, we did autonomous auto rotation for that.
I see.
So
yes, I remember that.
Yeah, so we switched off the motor, and it could actually just come vertically, or I mean, we did it in forward flight also and in hover also. And in that, I mean, we are able to do flare and all those things actually.
Right. So all you have to do is take that.
Right.
You just have to take that same control system and that swash plate, and to your rotor blades, where they're attached to the hub, just add another attachment which has a skewed hinge, and then that's all you'll have to do.
Right. So let's see if audience have any questions.
Hello, sir.
Yeah, question.
Yes.
Go ahead. You can ask.
Sir, the problem statement is excellent, first of all. And second, I just wanted to ask, like, for example, if we want to do certain experiments in our own laboratory, so how do you manufacture those blades which has got custom made twists and taper?
Yeah, the advantage here is at this scale, it's very easy to make these blades. So only thin circular arc airfoil. So if you have a fiberglass layup or carbon fiber pre-preg, all you have to do is find
Hello, sir.
Let me show you this cross section again.
Yeah.
Okay, all you have to do is see this circular arc profile. That's the thick black line, right?
Yes, sir.
So all you have to do is find a mold that is a cylinder, circular cylinder.
So it doesn't have an
this
aerofoil cross section, right?
It doesn't need airfoil cross section because this is a very small rotor, right? And it's spinning up 2000 RPM, but the Reynolds number is still not that high. So you don't really need an airfoil shape. You just need a thin circular arc that will work quite well.
Okay. And
you're not going to stall or anything, right? So you just you'll work fine in linear regime of your airfoil.
And so like, sorry, sir. Sorry to interrupt.
So you have a circular arc airfoil. You can create this by putting up your layup on a cylinder, basically just a metal cylinder of the correct diameter. And depending upon the angle between the layup and the axis, central axis of the cylinder, you can introduce twist or no twist and so on.
Okay, sir. Okay, sir. I got that. Yes. Thank you, sir.
So these are still this carbon fiber made or glass fiber? The blades which you are
These are
using?
carbon fiber with, you know, we have some pre-preg, so we can make it.
Right. No, because they were
But it
very
needs-
flexible. So I was wondering, I mean, with the carbon fiber also, you're getting that kind of flexibility.
Yes, it's very flexible because it's very thin.
Very thin. Yeah.
That's why it's flexible and the blades bend all the way back and cross also.
And that was really amazing.
But
to
if
see.
you make it, what is that?
No, it was quite amazing to see your that snapshot of the video where it actually goes and crosses over.
Yes, we did not expect that. You know, it was quite surprising, but that's how it behaves when you have the high dynamic pressure. So what I was going to say is it is advantages in terms of flap, but when you decrease that flexibility so much, the torsional stiffness, you know, goes down and it introduces aeroelastic instability. That's the only other problem. It's a little bit of a challenge that you have to. So there's a trade-off. You need to make it stiff, but also not too stiff and not too flexible.
Just one more question I have is: have you looked at this two-bladed seat?
Two-bladed seat, I have not seen.
Oh, you've not seen? Okay. Maybe next time I come.
No, that's where there's a central. I know in Bangalore there's a tree that has it also.
Yeah, it's actually in Andaman. I mean, you have a lot of these trees. They are called helicopter trees, but the name is Gyrocarpus americanus.
Oh, I see.
Okay, and they have this two-bladed seat, which is way better than Samara seat actually.
Oh, I see.
Yeah, it has actually delta 3 coupling already built into it into the design of the seat.
Oh,
yeah.
I'll look it up.
Yeah, so I saw them actually when in 2015 I went to. Before that also, I mean, Professor Venkatesan had showed it to me actually. Yeah, so that actually is exactly this. I mean, it does exact same kind of auto rotation, and the seat spins at, I mean, some 5,000, 10,000 RPM. I mean, I don't remember the number, but it's pretty high. I mean, RPM.
Oh, I see.
Even small seats and two-bladed, the blades are actually curved, and the moment it starts spinning, it will flatten out. Otherwise, it will be somewhat like this.
Right.
Yeah. So very fascinating. Actually, we at one point I started looking at it. I mean, but then the student, I mean, she got admission somewhere else, so she left on the actually hung in limbo. But
right.
It's very interesting thing, yeah. Because you have done pretty much, I mean, all those things already. So I mean, you probably would want to look at that seat.
Yes, I did not know of that one, but
yeah, next VFS I'll bring some seats for you. I have actually quite a few of them in my.
Okay, very good.
Yeah.
Hello, sir.
Yes.
Yeah, Kushal, go ahead.
So one more question. I just wanted to ask, like, as you mentioned, there is cyclic control. Am I right, sir?
Yes, there is.
So, sir,
in the prototype that we launched from the pneumatic cannon, there was not any cyclic control. But in the one the final video I showed with that had cyclic.
So how is it possible to have a cyclic control without swash plate? Like, I might be wrong. Is it possible to have a cyclic control without swash plate?
Well, this has a two-dimensional swash plate, so it's like a swash plate, but it doesn't go up and down. It only goes in one plane.
Okay, sir. Thank you, sir.
Any more questions from audience?
I see one here in the chat. It says, "Can the payload be made to spin? Can the payload be made to spin along with the rotor, thereby eliminating swash plate for cycling?" Yeah, that's interesting. There is a little bit of a problem introduced when the whole body spins, and one problem is that it takes a longer time for the whole rotor to reach its steady state in terms of rotational speed, because you're basically increasing the inertia of the whole system. Rotational inertia increases a lot when you start making the body also rotate. So if you don't care about how long it takes to reach the steady state, if you're dropping from very high, then maybe that's okay. But if you're dropping from a low height, then it will take too long to reach its steady state. And another problem is that the whole thing will now act like a big gyro. It'll have a very large angular momentum. So if you want to introduce any changes in its trajectory, you have to overcome a lot of these gyroscopic couplings. So if you have a very light rotor, spins up fast, you have very small angular momentum, and you can overcome that. Or you can have two coaxial rotors spinning in opposite directions to cancel the angular momentum. That would be the advantages. So that's why we try to avoid making the body spin and put the whole rotor on these bearings.
Thank you, sir. Got it.
Okay.
Any more questions from?
So I couldn't hear any of that.
Yeah, there is some interference from somewhere. Where is this interference coming from? I mean, everybody is muted. If any other question is there, please type. Okay, I think we are already done. So thank you so much, Sir Sirohi, for this really wonderful talk once again. Okay. Every time, I mean, I get to see the research going on in your lab. It's so fascinating and really encouraging. And interestingly, because I mean, this problem started way back in Maryland, long back, and now you have made tremendous progress in that. So it's really, I mean, exciting and heartening to see that. Okay. So thank you so much for sparing time so early, so thank you all the participants for staying up late. It's 8:30. So thank you, and
thank you all.
yeah. So I'll,
okay. Good night.